Good afternoon, and thank you for joining today's presentation. I'm here at the Center for Mathematical Sciences, sharing my research, which is based on a 4-year research project on smart factories. Most of the companies that we dealt with are from Denmark, and I'm now currently working in the Institute for Manufacturing in Cambridge University, and I specialize in information systems. Quick background about my work and discipline. I have a background in mechanical engineering. Therefore, I come from a more physical world where automation of systems has traditionally been more about robotics and machine equipment. However, with the latest advancements in digital technologies, there has been a lot of talk about how the advanced digital technologies and computer-based systems can be used to automate these factory operations. My current research interest is to design digital interventions for supply chain operations for problems outside of my discipline. And I'm working on a food security project currently. So today's presentation follows a very traditional sequence. First, I'll start introducing the topic on what we have studied, and I will then end it sharing what we found and what our results are. So before I get started, I just wanted to give a quick introduction to the context. So I am presenting the research that is very closely related to Industry 4.0, which is a fourth industrial revolution's concept. Industrial revolution started right here in England in 18th century, and on the left side of this pane, you can see a print that is showing the steam-powered cotton factory. So this was when the first industrial revolution happened with the beginning of mechanization. So the second one was again very distinct due to Fordism and mass production, as it benefited mostly from the invention of electricity. And the third industrial revolution, which happened in 1970s, already started to see some sort of automation and computers. And the current revolution, which is, we all call it fourth industrial revolution, is an ongoing step forward in a direction towards cyber-physical production systems. So with more intelligence and more use of data. So the smart factory is a concept that comes from this fourth industrial revolution, and smart factories are known to have high degree of autonomy, and they also have cyber-physical production systems. So that's basically the concept of a smart factory. And smart factories do exist in real world, and they serve many purposes. And one of the purpose being supply chain disruptions when they happen. If the factory is very well equipped to handle this sort of disruption, it is able to manufacture the goods within a very short period of time. And one such example I could give you is Moderna, which is a vaccine that we all know. We probably remember that COVID happened some time ago, and the whole world came to a halt, and most of these supply chains were completely disrupted. Food and many essential goods were very difficult to procure. So during this time, vaccination was another important product that we were all desperately waiting for. So some companies like Moderna, what they did was they were able to produce vaccines in large volumes soon after the virus's genetic code was released. So in that chaotic situation, they were able to very successfully manufacture and send it to different parts of the world. So this probably shows how efficient their supply chain was. And they were, of course, using a lot of Industry 4.0 technologies, and their factories are quite smart. And so this is one example on how smart factories are beneficial. So the backbone of smart factory is Industrial Internet of Things. This is the concept I would be talking more throughout this presentation, because industrial IoT is enabler, and it's a network, a web of connected machines and products and services. So with all, it has a goal to fulfill a manufacturing target. So coming to the agility part of it, why do we need this sort of flexibility and preparedness for supply chain disruptions? So we see that real world is not very quite balanced, and it is quite chaotic, and most of these systems, such as sometimes traffic, and on the left in this picture you can see, and there is a beautiful flock of birds. All these are not taking instructions from a centralized system, and they are able to talk to each other, and they're able to handle a very complex situation with some amount of autonomy and cooperation to get things done. Despite non-compliance of how this traffic might look very chaotic, accidents might not always occur. That's also because the drivers of these vehicles are communicating with each other, and they are coordinating with each other. In computer science department, in discipline, this kind of principles are very common in distributed artificial intelligence systems. They're also called as multi-agents. So in manufacturing field also, we have these concepts which are also called as holonic manufacturing systems. But I mean, imagine if a factory is also operating in a manner where the machines and the equipment inside the factory are as autonomous and as decentralized. So they are able to coordinate with each other to fulfill a production goal. So to make that happen, it's very important to have proper digital technologies. So even though these factories that we are talking about are all not new, most of the companies have legacy equipment, meaning old equipment. They are not very equipped to do these modern operations like we want them to. Therefore, it's very challenging to make them, modernize them, because these equipment cost millions and billions to all these companies, and they're not going to throw them out simply because there is a new technology that's come up and there are new requirements. Therefore, the enterprise information systems, which is also an important field in information systems literature, comes into a picture. So enterprise information systems are basically the software systems. In information system field, it not just includes the software, it also includes the user and the task. So the idea is to collect, process, store, and distribute the enterprise data. So these enterprise information systems are many all over the world. For example, human resource information systems are commonly used by competence management and HR departments, whereas in manufacturing, the manufacturing execution system is a very important system that is known to hold a lot of data that is in the factory. So our project is mainly focusing on the manufacturing enterprise information systems. So I would like to, before going further, give a small introduction to what happens in a factory. So factories have very complex operations, as we all know. And there are many standards that define the language of how the information and processes work in a factory. And ISA, International Society of Automation, has come up with a standard called ISA 95, which is a very popular automation standard that describes how the systems have to be arranged and how they should be managed and designed to make efficient and effective flow of data between these systems. So if you see in this picture, the uppermost layer has IT systems, which can be like our computers, where it's a piece of software and it might not have direct linkage with production equipment. Whereas the most bottom part that you see is called operations technology, that is connected most of the times to physical devices. So basically the operation technology controls the physical devices directly. Whereas the middle layer is something that's like a bridge between the lower level and the higher level. So the data that's available even in the most bottom layer of a factory can be extracted using these middle layer. So the middle layer, which is the enterprise information system, or which is MES, is very essential. So it's important to design them and modernize them to extract as much data as possible and make best use of it for in the context of fourth industrial revolution. So our project has a very focused objective, which is to derive some design principles for an information system to enable a smart factory. So as I initially explained, a smart factory is meant to be handling supply chain disruptions, and it should make the factory flexible. So let's just look into how companies want flexibility and why do they want flexibility. In this picture, you will see that there is a mini figurine, which is a Lego, a mini figurine. It has many different parts. There is sword, and there is a hat. There is also different kinds of jackets. So these are different things that make a mini figurine. And Lego is offering products as per customers' requirements and customers' needs. If I want a different kind of hat, I can order it and they have to produce and send it. So this is very challenging when we have to think about from a manufacturing point of view. If they ask, before we are more used to mass producing and sending it to the market, but now it's more customer driven. So this concept is already called as mass customization. However, the challenges are getting even more and more complex because of all kinds of geopolitical problems and also material availabilities and cost and all these issues. So every company these days, very large companies, they all want to have as much manufacturing flexibility as possible. Therefore, we wanted to study in our project using a real world example. So we worked very closely with these 3 large companies that are based in Denmark. I think you all know Lego, which is toys manufacturer, very iconic brand, and Danfoss, which is also like a heating equipment manufacturer, and Linak. So these 3 companies are very much interested in flexible manufacturing for the issues that I just explained. They also want to deliver their goods faster, and they want to make as much customizations as possible. So we wanted to bring that relevance aspect into our research. So we worked closely with these companies throughout our project. And we also, on the other hand, tried to manage the scientific rigor as much as possible. And we have chosen our research to be in design science framework. So design science is suitable for research in the engineering field because it creates a framework that also draws a lot from the real world. So we are not just sitting in our own offices and working on trying to solve the challenges that are existing in the factories. So this is more abductive in nature, and the artifacts are what in a book called, the Herbert Simon is the founder of this. He's a big thinker in this design science area. So he suggests how artifacts are the outcomes of this kind of research. And there's a whole big line of thinking and like a philosophy around it. So we wanted to follow that because we wanted to cover, we wanted our study to be very abductive, not very deductive, because it's more to do with design principles. So that's basically our framework. And this is the theoretical framework of our study. We have drawn from 3 large areas of research. The first one is reconfigurability in manufacturing. That's more to do with flexible manufacturing literature that comes directly from operations management and supply chain management field. Whereas the design principles of smart factory are more in the computer science and a lot more in the industrial automation, in newly emerging field of Industry 4.0 literature. And the third aspect is ISA 95, which is an industry standard. So we've used these three to answer these questions. And how does information system needs development? The development of IS involves system design. And system designs are two types. One is very high level, the other is very low level. The highest level is like a blueprint, and it should guide the designers on how to develop the data model. And most of the time, this sort of information comes from qualitative studies and trying to get some data from the users, going to the domain, which is manufacturing sites, and talking to the people who are using these systems in factories and understanding their needs. So we have to first design the requirements and then go on to design the system. So the second part is low-level design, which expresses the logical detail, and that's more relevant to the programmers. So in our research, we are talking mostly about the high-level design, even though our project had people with low-level design focus who designed systems and designed the data models. So ISA 95 standard provides all these functions and different kinds of models to make this happen. So we use that. So this is the background about the system design. The methodology we used was very iterative in nature. So it was something where we had used a lot of case companies. So it was case study based, and it also had a very large emphasis on having the artifacts. So the first phase of our research was requirements gathering. As you can see here, there are 6 large companies we worked very closely with in the span of 4 years. And all these companies have very specific goals with respect to smart factories. And they have all been very much involved in enterprise information systems, implementation projects, and Industry 4.0 projects. So we tried to engage them. These were our stakeholders. So we have done a lot of interviews and workshops, as well as field visits. We used their we studied their company reports, and we interviewed them. So with that data, we were able to gather some requirements to understand what the industry wants in this area. So as an example, Ala is one of our case company, which is world's largest manufacturer of organic products, one of the largest. It's a cooperative of thousands of farmers based in Scandinavia. And this company has been very actively involved in Industry 4.0 projects. So they have been driving digitalization even at the lowest level, which is at the farmers level and also at the dairy farms. So they value data a lot. So it was very useful for us to talk to them and to involve with them through presentations and to workshops to see how they are developing their systems to make this work. So like that, we moved to the next phase. So we did back and forth. It was iterative. And we tried to use this requirements gathering to specify requirements. So for that, we went back to our lab. This is Smart Production Lab in Denmark. So this is a state-of-the-art Industry 4.0 learning factory. So we worked there and we tried to use these physical systems to understand how the requirements can be specified. So that's how we also did some lab work. And then in the last phase was actually about the real design. And in that design part, we used QFD, which is Quality Function Deployment Method. So that's a very kind of popular systems engineering approach that many industrial engineers use. It was first invented in Japan, and it's quite widely used by many manufacturing companies and also in some other fields. So the idea of this grid is to translate design requirements between two very different fields. So we use that to understand how manufacturing requirements can be translated to IT requirements to design systems for our factory. And then we tried to use some standardized graphical language, such as unified modeling language for system modeling. This is a very computer science method. So it was very useful for us to use this notation for describing our systems and our ideas on how it should be designed. So there are many types of diagrams. There are structural diagrams, there are behavioral diagrams. So we used a few of them, like class diagrams and object diagrams, mostly structural diagrams. And then we also worked during the 4 years with all these companies to come up with some demonstrators, which are small-scale experiments to show how our scientific activity can be converted to a marketable solution. So in the first demonstrator, we tried to connect small robots and make them talk to our system in the highest level. And then in the second part, we used ThingWorks. It's an industrial IoT platform to to make it interoperable with the other systems in the factory. And in the last part, we also tried to demonstrate how, in case of Lego, a customized order can be fulfilled. Like if the customer is asking for a very specific variants, how is it going to be managed in the back end of the manufacturing company, and how that order will be fulfilled, like how the products will be produced and how the order will be distributed to different factories in the world to produce that product. So we have done this using some design sprints, and since it was iterative, we used a Scrum methodology, which is a part of Agile framework. And our findings, we had a variety of findings. So one of the main findings were not just artifacts and some knowledge, but also some conceptual frameworks. So to establish a common understanding and to understand what a smart factory capability is, we try to use concepts from both business and manufacturing domain and IT domain and combine them to create these conceptual frameworks. We've also, we were able to also come up with some tools. For example, the grid that you see on the right side of the screen. This is about establishing some kind of a common language to determine how to use these IT systems for manufacturing. And there are many types of principles. There are 4 main principles for designing smart factories. The first one is about information transparency, which talks about how timely and accurately information should be available throughout the supply chain. Whereas the second principle is about technical assistance. I think we all know how these days the generative AI models are working. So it has the same idea. It is about helping the workers on how to, assisting their tasks and using artificial intelligence to guide the workers in the factories. So decentralized decisions are mainly about how machines can take autonomous decisions. So that's the principle. Whereas the fourth principle is about interconnection, which is about connecting different entities in a factory. So an industrial IoT based interconnectivity is the foundation of smart factories. This is what we have concluded through our studies, because it's not to say that the other principles are less important. They are important in their own right. However, the industrial IoT based interconnectivity is like far more superior in a way, because it offers a holistic approach, as many companies will struggle to extract data from their old machines because they are not interoperable, and it's very hard to link them into a web of network. Therefore, we believe that once this hurdle is crossed, all the other bigger ambitious projects that a smart factory can perform can be unleashed. So to make this happen, the to build this network for common goal, sensors should be placed everywhere in the manufacturing activities, and real-time data should be flowing easily, and also intelligent decision making should be enabled through this. It also should use predictive analytics, and also there should be a seamless collaboration and autonomous control. This is one example of our design that incorporates IIoT platform, and this is another design that we proposed for a factory network architecture that also shows how these systems should be placed and how the communication should be secured between these systems to not have any cyber attacks, the proper authentication and cybersecurity protocols. And in this sort of presentation, we proposed factory systems and entities and their relationships using unified modeling language. This chart shows a class diagram that describes the entities and relationships between different systems in the smart factory. So this is the essence of our findings, and our contributions were mainly to find some consensus on using enterprise information systems for this purpose. So this is somewhat one of the first studies to very do in-depth research in manufacturing execution systems. And we have also understood the applicability of these systems in the presence of industrial IoTs. And it was also very empirically driven, meaning the companies were also involved in every step. So it had a high industrial relevance and collaboration. And the benefits were also kind of tested because we did these experiments in the industry setup. So the industry partners were also part of our team. And so the future work, there is plenty of future work that needs to be done. All these old systems that are legacy systems, they have to be designed in a manner that are flexible, and they should be designed in a manner that they are able to communicate with the other systems, the new modern systems. So that's a very big challenge because old systems are not designed for today's data age. So for engineers, it still remains a big challenge because we are not endorsing a factory that is brand new. We still want to make the old factories modern. Like that modernization takes a lot of effort. And just to reflect on this process, the idea is that machines need to communicate with each other, and they have to take their own autonomous decisions to create a highly efficient and agile manufacturing of the future. And also, we want to stress that an enterprise information system, a modern one, can revolutionize traditional manufacturing. It can make it more responsive, adaptable, and it can make help support manufacturing to changing market demands. So we emphasize that ISA 95 like industry standards must be used from the beginning on. So the systems are streamlined and there is a room for new systems to come into the factories. And also we see that companies can improve their productivity and they can reduce costs. They can also make their operations more sustainable using these practices. And the Industry 4.0 journey in every smart factory journey in companies can achieve these on a long run. And we advocate that using a standardized enterprise information system could be the first step. And designing and implementing a smart factory is a continuous improvement process. It requires a very comprehensive understanding of all the technologies that are involved in the factory, and it should be about like a use case basis, not like one night. It need not be so dramatic. So it should be like a continuous improvement. So with that, I'd like to thank my collaborators and supervisors and a lot of people who've helped me get this work done. And here are some references. And thank you very much for listening, and please reach out if you have any ideas or any questions. Thank you.